Hello. Yeah, we'll do little bit of chapter 5, and then what I did last tutorial, I went into one of the classes. I think their class. And I saw what's going on. So let's talk a little bit about how you approach a problem. Yeah. Something is missing. Some basic things are missing. Like when a problem is given, told you this already in the class, right? Once or twice. First you look at it. You have only 3 parameters there: P, V, and T. And then if you read the question which is there in English, you will understand whether it's an expansion or a contraction, whether you're heating or whether you're cooling, and whether the pressure remains constant or the pressure is changing if it has a spring. So until you do this PVT and write up down constant, up down constant, up down constant right at the beginning, and you have a problem. So firstly you should learn to identify what is at the beginning. The pressure is remaining constant. It has a certain volume and a temperature. The next step says I'm heating. So then you should write T. What happens? Increases. Then what happens to volume, obviously? Huh? Hello? What happens to volume? Louder. So if you write that, how will you get the trend correct? Haven't I told this already? First learn to get the trend correct before you put your pen on the paper and try to do the numbers and do all that crunching. If you get the trend correct, then quietly you'll write your PV diagram and TV diagram. Over, then you go do the numbers. Otherwise you're all over the place. You're simply thinking what to do numerically, what equation to use from the book, and no, what is that? What equation you'll use from the book? So this is what I kind of experienced in one of the tutorial classes. The idea was for me to hop to 5 different tutorial classrooms. Obviously I got caught in the first tutorial classroom. But ideally I want to come to at least 4 to 5 tutorial classrooms and see what you're doing. So initially somebody should ask, or you should ask yourself, what is given? I have a certain volume, I am at a certain temperature, I don't know the pressure, but it says I am saturated, so I can go to the table and find it. So these kind of things. You need somebody to prompt you, or can you do it by yourself? This is how you exactly do it. And there's not 100 things that are there. There's only P and V and T. This is what is there. You have not even come to U. If you get V right, you will never get U wrong. And if you get U right, you will never get H wrong. And if you get H right, you will never get S wrong. But the issue is, if you make mistake with V, everything will drop. So let me do that at about half hour. I'll give you a few schematics, I'll draw some things, I will ask you questions. Let me see how you approach it. But before that, let me just go a little bit further into chapter 5. So I think somebody nicely told that day, what is heat capacity? I like the way that student told it. So you're dispersing energy. It's how a material can take the energy. It's not exactly absorption, how it can disperse it. How it can disperse. Sometimes the total energy can be the same. You can go from a mildly dispersed state to a very dispersed state. So from a decently clean room to a very dirty room. Get it? There are a lot of entropy jokes. Whoever keeps a room dirty, like my office, that's called as a high entropy room. Yeah, that is our natural tendency to let everything disperse as much as possible, all over the place. So heat capacity has the same units of entropy. Then you should ask me the question, if it has the same units of entropy, then why we have two names, entropy and heat capacity? You want to answer that, or shall I answer that? Both have the same units. Entropy and heat capacity have the same units. So then your question should be, then why don't we just talk about entropy as a quantity that determines how much dispersion happens, or in your language, how much disorder happens, or how much randomness happens. If that's the case, then why do we have heat capacity? That's my question to you. Think of that question. 2 marks. I will draft the question myself. Heat capacity and entropy has the same units. If that's the case, why are we having two different properties? Answer the question. Yes. Because that's what your friend answered, right? That day he said it tells you how the energy is getting dispersed. Heat capacity tells you how the energy is getting dispersed. Then I talked something about stimulus and response, yes? Recollect that and answer the question. What's the difference between heat capacity and entropy? I already answered this last class. I talked about stimulus and response. You cannot measure something absolute. Louder. You can measure only change, but simply change cannot be measured until you give a stimulus. So what's a stimulus? Louder. We already went through this last class. Change in temperature, not temperature. Change in temperature. There's a difference between temperature and change in temperature. Yeah, you have to give a change in temperature. Then you'll get a change in dispersion of the energy. And what is the coefficient? That relates the magnitude of the response to the magnitude of the stimulus. Louder. Heat capacity. So that's how I do the experiment to even measure heat capacity of a material. Got it? Asked about the rock, right? I will go to a calorimeter and I will change the temperature slightly. I think, wasn't this all last class? Yeah. Go watch the videos. Why am I doing the last class rehash? So if you change the temperature, what happens? The material will respond and it can either give out a little bit heat or it can take a little more heat. Then what will happen to the temperature of that material? It will change. Then in the reference side, I will keep the same temperature of the sample. So I will either pump in heat or remove it. So that is how I know how much heat is given. So that's exactly by knowing that heat is how I will calculate heat capacity. Cp would be, so if I assume constant pressure, Cp would be dH by dt. H is nothing but heat flow. Again, last class, yes. So if I assume constant volume, there is no work done. CV is equal to du by dt. So we went through this, right? That's it. So I asked about, he answered, right, the question, why we should measure heat. When I asked about breaking the rock, correct? What did your friend say, sitting right there? What did you tell them? You said you will take a hammer and break it. Then you will calculate the work done. But then how will you calculate the energy? Again, not possible. So the best thing to do is see the change in the heat. So there's a term for it. What is that term? Enthalpy. I'm assuming PdV, so I'll just put it as P. So if it is constant volume, what happens? It's gone, there is no meaning for enthalpy. So all you consider is U. So then now go back and tell me again what is heat capacity. So I will change dt, that's the stimulus, and what will I see change in if it's constant volume? If it's constant volume, I'll see change in du. If I do, this is constant volume constant, pressure constant, I will change dt, what will I see change in? dH. So what's the coefficient? Heat capacity. So constant volume heat capacity is write the other one, Cp, dH by dt. Make sure you write the subscripts for your benefit so that you know you're talking about constant volume and constant pressure. So it's like your Young's modulus. Somebody nodded that day very vigorously when I said, what's the mechanical coefficient for Hooke's law? Modulus. So modulus is what? Not simply stress over strain. It is the change in stress over change in strain. Heat capacity is change in internal energy with change in temperature. There's a stimulus and then there is a response. In the mechanical thing, you can give stress and you will get deformation, or you can give deformation and you can see the change in resistance. So, got it? Same thing. Ohm's law, Hookean law, this thing, everything is analogous. Yes. Just don't say it is absolute values. It's not absolute values, it's change in values. Otherwise, there's no meaning to stimulus. Stimulus means you have to change something. Only then you will see a change as a response. Okay, there's nothing very difficult, I think. So conceptually, how do we understand? So you anyway said it's dispersion of energy. So in the material, I talked about clean air and polluted air. Last class, again. Hey, what am I doing? Going back to last class over and over again. So conceptually, what does heat capacity tell you? If today the heat capacity of air, your ambience, atmosphere is high compared to yesterday, what will you understand from it? So first thing, you will, like onion layers, you will say that it's dispersing better today, correct? Okay, then I will ask you onion layers, what does that mean? What does that mean? No, today's heat capacity is more than yesterday's. So if I ask why, you will say today it is dispersing better. I got that part. Then I will ask, what does that mean? So what do you think is happening in air? For it to disperse, what it should do? Louder. So expand becomes a very organized, oriented work. So it becomes order. Yeah? As soon as you say expand, your friend will ask, it's a vector, give me the direction of the expansion. So that means all the molecules came together and expanded in one direction. So what will that do to your dispersion? Will it increase or decrease? When you get oriented, will your dispersion increase or decrease? Decrease. So nature won't do that. Spontaneously, nature won't do that. Room will not get cleaned up spontaneously. Room will in fact get dirty and dirty spontaneously. Come to my office one time. Especially today, you can come and take a look. It's gotten worse. It's like a pigsty. So expansion is tricky business. You should not go to work. Work will orient everything. If you orient, your natural random dispersion will decrease. So now, today heat capacity is more. What do you understand from it? Good attempt. You made a good attempt. So at least he said something. Expand means he's actually thinking something else. He said the wrong word, but so that's basically my question is implicit. That is implicit in my question. Thank you. Entropy obviously is changing. So is it increasing or decreasing? Increasing. So then how it increases? If that randomness, the disorder increases, what should it possess? Today, what is so special that it possessed? Louder. You got to give him 1,000 points. Yeah? The mobility is much higher today. So it's dispersing really well and it has a very good Brownian random motion. Yes? So the heat nicely gets dispersed into small pockets. And you have to pump in more heat to see friction and to see your definition, change in rise in temperature. So that is what you will get. So what did I tell last class? That you will understand very well. You should. But you cannot tell who made it happen. Got it? And how it became. So there you have to calm down and be cautious. Yes? You can say mobility increased, but you cannot say whether nitrogen's mobility increased or whether oxygen's mobility increased, or no, that you cannot tell. But you can in a way also tell that yesterday something was clustering together, today it is dispersing better. So if you come to the real world a little bit, you can think maybe the pollution might be less today. Maybe the pollution is less today. That's a guess you can make, because heavier particles will always try to cluster together. Like carbon, like even SOx, NOx, there are also heavy gases there. So you literally can see those colloidal particles from the exhaust, right? From the vehicles. One time put your face there, you'll get black stuff under your eyes. So that's the beauty of heat capacity, and calorimeter is used to measure the heat capacity. So maybe one of the most fundamental properties that describes your universe, heat capacity. And it is, if you don't say specific heat capacity, it's an extensive variable. It depends on how much material is there. Yes? It's an extensive variable. So now, obviously, it's all going to be question hour. What is the trend of heat capacity? If you increase the temperature, what might happen? Will it decrease or will it increase? Will your dispersion increase? Your ability to disorder more, will it increase? Basically, your word, entropy, you said. So will it increase or will it decrease if I change temperature? When I say change temperature, I'm going on the upward trend, increase temperature. So what would be a natural trend of heat capacity versus temperature? Is it increasing with temperature or? Heat capacity is an intrinsic property of the material. but it's also a function of temperature. For that one temperature, it's an intrinsic property of the material. But with temperature, thermal activation will change, correct? The degree of thermal activation will change. So when that changes, your heat capacity also will change, your thermal conductivity also will change, all your thermodynamic, your fun properties, thermal expansion coefficient, everything will change. So what will happen to heat capacity if you increase temperature? Huh? You know why I'm asking, right? Because I know somebody will say decreases. That's why I'm asking. What will happen if I increase temperature? The mobility increases or decreases? Louder. So then what will happen to heat capacity? Increases. That's why I asked. I'm just double checking again. Same question in another way. It increases. Most of the materials increases. There's one or two exceptions. So then the state of the material, you go from solid to liquid, would the liquid's heat capacity be higher than solid or vice versa? Liquid will be more than solid. Obviously the mobility of liquid is, so then gas and liquid? Gas. So then can you little bit write down what are the factors that influence the heat capacity? That would be your take home for today. You write it yourself, then I will add if something is missing. Start off, loudly tell me. Factors that affect CV or CP. Yeah. You can rehash what we just discussed now and you can start with it. Yeah? Very good. He went with the most important one. Temperature, mobility. For that, what would you want to use a general word? State. Very good. Depends on the physical state. You write it, PHY state, however you want to write it. Next. I will tell and then next your turn. Now my turn. The type of composition that you have, because that will control the mass of the molecules. That will also alter your diffusional mobility. So my thing is composition. So heat capacity of 10% sugar and water will be different from heat capacity of 40% sugar and water. Yeah? Composition. I put up composition. Your turn. Very good. He went to microstructure. Excellent. Maybe one of the most important things. So that will play a huge role in solids. So crystalline solids are ordered, amorphous solids are more disordered. Which one do you think commonsensically will have higher heat capacity? Amorphous. Very good. Call that as microstructure. Very nice. So now you know exactly if somebody says like your Black Panther movie, all of us want high energy capacity materials. We want materials to have high thermal capacity, high mechanical capacity, high electrical capacity. You exactly know what is the skeleton of what they are talking about. That material should have what? Otherwise, nothing. That sentence is of no use. So go and watch Black Panther again. It's a material science movie if you really look at it. It's very obvious. So that guy always talks about high energy materials. It can be electrical capacity, mech capacity or thermal capacity. These are the three things we usually worry about in our product development. So if you're even writing a very basic hypothesis, if I want high capacity materials, what should my materials be like? What should they possess? Your first one phrase that you will write. You already told it, already mentioned it today. It should be very mobile. You should have a mobile solid. Yeah. If things don't move, then you cannot hold. That's it. I think so. One class I told you it's about moving and blocking. So there's only two phenomena that happens common. So if you have moving, you will get a lot of energy dispersion. That's it. You need high mobility materials. Shall I go to your little bit? 4th chapter. Ask you a few questions. Yeah? Okay. Let's see how you approach. So treat this like a tutorial now. I'm going to chapter 4. So heat capacity is more or less done. I will come back to chapter 5 problems on Saturday. Now today you have a test, don't you? Okay. Then I'm sure you are all primed up. Say yes. Okay. So let's see how you work. Okay, there is a material. So the first step, so this is how the question is. There is a certain material and the first step is at constant volume I will increase the pressure. By doing fill in the blanks. First step, for a given material at constant volume I will increase the pressure by doing fill in the blanks. Louder. Say heating. Yeah. Is that what you are trying to tell? Okay, then how do you approach this? In the beginning, what do you write to yourself? Assume you are in the tutorial. So first I will ask you, what is the material? You will say some refrigerant R139. Okay. Is the volume constant? So then what do you do? And then the question itself says the pressure increases. So what do you do? By doing what? Second step, after it reaches a certain pressure, the volume continues to, now the volume increases by expanding, and I am doing what? No, I know I am doing work, but did I cool? Did I cool or did I continue to heat? Did I cool or did I continue to heat? So there are two questions. How did my pressure that was increasing suddenly became a constant? No, it was not expanding, you see. Pressure was, it was constant volume to begin with. No, in the first step, the volume is constant. You add that much in a small container. And then you just increase the pressure by heating. How does the pressure become constant? Only if you close the lid. Yeah? If you close the lid, will the pressure become constant? It was constant volume. Yes. So in the beginning, when the constant volume was there, the pressure increased. Was the lid closed or was the lid open? Okay. Can you write it for yourself? So then in the next step I said, I continue to heat and it begins to expand at constant pressure. Then what I might have done? I open the lid. Excellent. I open the lid. Got it? Second step, I open the lid. So first step, if you close the lid only, volume is constant. So then in the second step, I'll ask you in the tutorial. So what happened to pressure? You open the lid. What happened to volume? What happened to temperature? So you cannot get the trend wrong. Got it? So you have to do this in a problem. Simply just staring at the question and just looking at it doesn't do much. Then you'll randomly pick something and try to use PV equals nRT and make some guess like V is given, this is not given, so then it must be that, and then I will tell me I'm imagining something. Isn't that what you do? Even if you do that, at least you know we are talking about only three things, P and V and T. So at least you should calm down there. Yeah. Next problem. Good? Shall I go to the second one? Okay. Oh, by the way, you write the PV-TV diagram for this? For the two steps, I will write my PV here. Da da da, da da da, da da da. 1, 2, 3. So he said work done, right? For the second step, you will have the work done. So 2, 3, you will, from the rectangle, you can calculate the area under the curve. How will the temperature go? No, volume is constant in the first step. So temperature will, sorry, it's a vertical line, okay? Vertical line and then some angle. It's a ramp heating. You're ramping all the time. Again, label it 1, 2, 3. That's why you practice this, because you cannot work so slowly in the exam. You will not complete the paper. One thing I'll guarantee you a little bit, if you didn't know, the number of questions will always be little more in number. Got it? You have to work a little bit faster. Don't try to learn there. In the class, you will not finish the problem. Practice this and come PVTs. It's very simple. So are my PV-TV diagrams okay? Okay, moving on. Second one. What these guys are doing that day. I'll go with their problem. No, I want to go with another problem. First, let me see whether you understand these diagrams. Hey, what happened? I have no idea what. Oh, what is that? Oh. Now what is this? Oh. What is that? Okay. What is this? Huh? What? Some material. Okay, now how is it standing there on top? There is enough pressure to hold it there. Yes? So how will you calculate that pressure? Both atmospheric pressure as well as the mass of the piston. So can I write in the beginning P is? Yes? V? In the beginning V? Constant. Yes? Everything is in equilibrium. T? Obviously constant. Now the piston will come and hit the stop. How do you make it happen? Sure? No, I'm just asking sure. You said cooling. I'm just seeing whether you're decisive. That's all. Cooling? Okay. So what happened to volume? Very good. What happened to temperature? Decreased. What happened to pressure? Why? Why? 2 marks. For that question I will put special 2 marks. Because for volume decreased, I hope you will tell me now the shading will go away here and this will come down. Correct? I hope you will do that. And then you will say automatically it cannot come down because I have to cool it and contract the material. Correct? That is how the piston will come down. Why the pressure remains constant if I ask you for 2 marks? Huh? The piston is always there at the top. So that is not changing, correct? So the pressure will always remain constant. Very good. So now can you write? First step, what happened? Cooling. V. T. P. Now you hit the stop. What happens if I further cool? What happens if I further cool after it hits the stop? Once again, slow down. What happens? So I said cool. First you go for the easy one. The temperature will do what? Decrease. Okay. Volume? Volume will be constant if I further cool. Huh? Huh? Okay, for that you have to justify though. Right, but the material can densify itself, right? Piston need not push and change the volume. The material itself for change in temperature can densify, wouldn't it? Shouldn't its density change, its specific volume change. I'm just thinking loudly. Since you very quickly said the volume remains constant. Correct. It hit the stop, got it, but then you keep on cooling further. So why it should occupy the same volume? If you're changing the temperature, shouldn't its density change? Then shouldn't its specific volume change? I'm not thinking proper. It's a valid question or no? Huh? Then you ask yourself that question. No, no, why extreme? When you change temperature, the density of materials will change, right? Even if it's a superheated vapor, once again, even if it's a superheated vapor, that's why we have the tables. If you change the temperature for a given pressure in superheated vapor, what happens? The volume also changes. Yeah, go. No, it's always controlled mass, isn't it? Why only after it hits the stops it has to be controlled mass? Yeah, this is always a controlled mass problem, correct? So the question is, only after it hits the stop and you continue to cool Temperature decreases, completely agreed. What happens to V? So it may not phase change. Let me put it that way. You cool it, but it need not phase change. Even if it phase changes, volume should change, correct? Then what happens to volume? Okay, you want to take a break from volume, it's fine. What happens to pressure? What happens to pressure? What happens to pressure? You're cooling further, what happens to pressure? Increases, decreases. But if it's densifying and the volume is changing, how pressure will decrease? Yes? Is that a valid question? No? That is like phase change only. If water becomes ice and vapor becomes water, density is changing, then pressure will, impingement will increase. Go. Yeah, collisions with the walls will be less. That's also one way to look at it. No, but when you write your PV diagrams where you're phase transitioning from a liquid state to a vapor state, do you start with high pressures or low pressures? And then what happens as you transition to vapor? Then if you look at it that way, then impingement should increase if it becomes a gas. Correct? So it's not exactly the impingement on the wall, it's the impingement on each other of the material. That's the pressure. Got it? And when they cannot take it further, they will impinge on the wall. And if there is a movable piston, they will try to push it. So it's not just pressure being exerted outward, it's pressure being exerted inward. That's how you write your phase diagrams when you start on the PV diagram. You start at water, as you always start from high pressure, and then if you apply vacuum, you can convert water to vapor if you decrease the pressure, correct? Freeze drying, we went through freeze drying. You can sublimate from water to. So here, what should I give in the question so that you don't get caught like this? When I say now, after it hits the stop, I further cool, and then what should I tell in the question? I further cool, and then what should I tell? I should tell that the changes in the density is negligible. Then I get it, the pressure will get it. So this is where I think most of you will get caught in a constant volume situation. I know most of you will get caught in the constant volume situation. So just double clarify in the exam, put your hands up and ask question. Get it? If the question is not very clear, So it is a constant volume situation, the second one. Yes, otherwise the P will not go down. Yes, okay. So let's write the second situation. I further decrease T, volume, P. Okay, now you can write the PV diagram. Write both the PV and the TV diagram. Careful, the only difficulty is in the constant volume place. Changing volume is easy. Telling you right now. One time write the PV and for this and take off. Good luck. I'll catch you guys Saturday.